ghost leg occurs when a current-carrying conductor is not properly connected to a ground reference, resulting in a false voltage reading on a voltmeter. In this case, there is actually a ground fault on one of the phases, but the connection between the faulty conductor and the grounding electrode is weak or intermittent. When the phase conductor makes intermittent contact with the ground, it creates a high resistance path for current to flow to ground. The remaining two phases have a full path to ground through the distribution system. The voltmeter measures the voltage between the phases. However, when the faulty phase makes contact with ground, it creates a potential difference between itself and the other phases. This difference can be enough to register as a voltage reading on the voltmeter, even though the faulty phase has no direct path to ground. To troubleshoot a ghost leg, firstly, check the grounding system. Ensure that the grounding electrode is properly connected and that there are no loose or broken connections. Secondly, measure the voltage to ground on all three phases simultaneously. If the voltage to ground on any phase is significantly lower than the other two phases, it indicates a potential ghost leg. Thirdly, use a clamp meter to measure current. Clamp the meter around the faulty phase conductor and the ground wire. If there is significant current flowing through the ground wire, it confirms a ground fault. Fourthly, inspect the wiring. Look for any loose or damaged connections, especially in junction boxes or panel boards. Once the ghost leg has been identified and corrected, the equipment can be tested to determine if it has been damaged. If the equipment is still not working, further troubleshooting may be required to identify the root cause of the failure. Electricity always wants to find a path to ground. A ghost leg occurs when there is a ground fault that creates a false voltage reading. Proper grounding is crucial for safety and to prevent ghost legs. To understand a 240-volt three-phase system, it's important to first grasp the basics of three-phase power. In a three-phase system, there are three alternating current sources that are offset by 120 electrical degrees. This means that the voltage in each phase reaches its peak at different times. This configuration provides a more consistent and efficient power supply compared to single-phase systems. In a 240-volt three-phase system, the voltage between any two phases, also known as the line-to-line voltage, is 240 volts. The voltage from any phase to neutral, also known as the line-to-neutral voltage, is typically around 139 volts. This is because the line-to-neutral voltage is the line-to-line voltage divided by the square root of 3, which is approximately 1.732. When measuring voltage in a three-phase system, it's crucial to use a voltmeter that is rated for the appropriate voltage range. Also, ensure that the voltmeter is properly calibrated to provide accurate readings. Start by measuring the voltage between each pair of phases. In a healthy 240-volt three-phase system, you should measure approximately 240 volts between phases A and B, phases B and C, and phases C and A. Next, measure the voltage from each phase to ground. In a properly grounded system, you should measure a relatively stable voltage from each phase to ground. This voltage will depend on the specific grounding configuration of the system. If you encounter a situation where one phase shows 0 volts to ground and continuity to ground, while the other two phases show 240 volts to ground, it indicates a potential problem. The fact that you measure 240 volts phase to phase in any combination suggests that the three-phase source is still present. However, the 0 volt to ground reading on one phase, along with continuity to ground, points to a ground fault on that phase. A ground fault occurs when one of the phase conductors comes into direct contact with ground. This can happen due to damaged insulation, loose connections, or equipment failure. When a ground fault occurs, the current from the faulted phase flows to ground, creating a low resistance path. This can cause the voltage on the phase to drop to 0 volts to ground. The presence of continuity to ground confirms that there is a direct electrical connection between the faulted phase and ground. The term ghost leg is not a standard technical term in electrical engineering, but it seems to refer to a situation where a voltage reading appears unexpectedly, possibly due to a floating ground or a high impedance connection to ground. The situation you described does not appear to be a ghost leg, but rather a clear ground fault on one of the phases. If you suspect a ground fault, the first step is to de-energize the circuit. This is crucial for safety and to prevent further damage to equipment. Once the circuit is de-energized, visually inspect the wiring and equipment connected to the faulted phase. Look for any signs of damage, such as burnt insulation, loose connections, or physical damage to equipment. Use an ohmmeter to measure the resistance between the faulted phase conductor and ground. A low resistance reading indicates a direct ground fault. If you cannot visually identify the fault, you may need to use a fault locator to pinpoint the exact location of the ground fault. A fault locator sends a signal through the conductor and detects the point where the signal leaks to ground. Once you have located the ground fault, repair the damage and replace any faulty components. Ensure that all connections are tight and that the insulation is properly restored. After making the necessary repairs, use an insulation resistance tester, also known as a megometer or megger, to verify that the insulation resistance between the phase conductor and ground is within acceptable limits. A high insulation resistance reading indicates that the ground fault has been properly cleared. Finally, re-energize the circuit and verify that the voltage readings are now normal. You should measure approximately 240 volts between each pair of phases and a stable voltage from each phase to ground. If the voltage readings are still abnormal, there may be other underlying problems that need to be addressed. To prevent ground faults, it's important to follow proper wiring practices and regularly inspect electrical equipment. Ensure that all wiring is properly insulated and protected from physical damage. Tighten all connections regularly to prevent loose connections. Use ground fault circuit interrupters, or GFCIs, in areas where there is a risk of ground faults, such as wet locations. Implement a regular maintenance program to inspect and test electrical equipment. This can help identify potential problems before they lead to ground faults. If you are not comfortable working with electrical systems, it's best to consult a qualified electrician to diagnose and repair the problem. Working with electricity can be dangerous, and it's important to take all necessary safety precautions. The equipment may not be working because of a shorted winding to ground. If this is the case, then one of the supply lines will measure 0 volts to ground and have continuity to ground. The other two lines should read 240 volts to ground. All three lines, read phase to phase, should measure 240 volts. Disconnect the equipment and then check the supply lines again. If the supply lines now measure correctly, then the fault is within the equipment. If one of the supply lines still measures 0 volts to ground and has continuity to ground, then the fault is in the supply wiring. I would recommend checking the ground connections at the equipment, the disconnect, and the panel. A loose or corroded ground connection can cause all sorts of problems. I would also recommend checking the neutral connection at the panel. A missing or loose neutral connection can also cause voltage imbalances. Also, it would be a good idea to measure the current on each phase with a clamp-on ammeter. If the current is unbalanced, it could be a sign of a problem with the equipment or the supply wiring. The problem could also be with the equipment itself. A shorted winding in the motor or transformer could cause a ground fault. The equipment should be inspected by a qualified technician to determine the cause of the failure. Remember to always follow safe work practices when working with electricity. Always energize the circuit before working on it, and always use properly rated personal protective equipment, or PP. In a 3-phase 240 volt system, you should have 240 volts between any two phases. The voltage from each phase to ground will depend on the grounding configuration of the system. In a corner grounded delta system, one phase is directly connected to ground, so the voltage from that phase to ground will be 0 volts. The voltage from the other two phases to ground will be 240 volts. In a Y system, the neutral point of the Y is connected to ground. The voltage from each phase to ground will be 240 volts divided by the square root of 3, which is approximately 139 volts. The fact that you are reading 0 volts from one phase to ground and continuity to ground indicates that there is a ground fault on that phase. This means that the phase conductor is directly connected to ground, either through a short circuit or a low resistance path. The voltage from the other two phases to ground is still 240 volts because they are not directly connected to ground. The voltage between any two phases is still 240 volts because the three-phase source is still present. To troubleshoot this problem, you need to first energize the circuit. This is very important for safety. Then, you need to disconnect the load from the circuit. This will help you isolate the problem. Next, you need to use an ohmmeter to measure the resistance between each phase conductor and ground. The phase conductor that reads 0 volts to ground should have a low resistance reading to ground. This confirms that there is a ground fault on that phase. The other two phase conductors should have a high resistance reading to ground. This indicates that they are not directly connected to ground. Once you have identified the phase with the ground fault, you need to trace the wiring to find the location of the fault. Look for any signs of damage, such as burnt insulation, loose connections, or physical damage to the equipment. Once you have found the location of the fault, repair the damage and replace any faulty components. Ensure that all connections are tight and that the insulation is properly restored. After making the necessary repairs, use an insulation resistance tester to verify that the insulation resistance between the phase conductor and ground is within acceptable limits. Finally, re-energize the circuit and verify that the voltage readings are now normal. A ghost leg is a term used to describe a situation where a voltage reading appears unexpectedly, possibly due to a floating ground or a high impedance connection to ground. However, in this case, the 0 volt to ground reading and continuity to ground on one phase indicate a clear ground fall, not a ghost leg. It's important to note that working with electrical systems can be dangerous, and it's important to take all necessary safety precautions. If you are not comfortable working with electrical systems, it's best to consult a qualified electrician to diagnose and repair the problem. The code reference for grounding and bonding is NEC 250.